In this activity, we're going to explore the atmospheric concentrations of CFC using data and a model. CFC stands for chlorofluorocarbons, and our particular focus will be on CFC12 for two reasons. One, as you can see from this graph of data extending through about 2008, CFC12 has the highest atmospheric concentration of all the CFC molecules. The other reason is that the atmospheric lifetime or residence time of CFC12 is 100 years. So it makes for an easy number to use in our exploration. So the first part of the activity is to look at data, and then in the second part we'll use a model similar to our water tank model, where we have an inflow of atmospheric CFC into the atmosphere. So C would be the content or concentration of atmospheric CFC12 in the atmosphere, and the removal rate would be just whatever concentration is in the atmosphere divided by the lifetime, or divided by 100 years. We'll explore that in part two. But in the first part, we look at real data. And in this graph, this is data from the National Oceanic and Atmospheric Administration on CFC levels using flask samples. And here we have a larger figure. We can click on this and see the data a little bit more clearly and read the graph. The red values here are the northern hemisphere values. The green triangles are Mauna Loa, and the blue squares are in the southern hemisphere, America's Samoa, and then there's some data from Cape Grim and the South Pole. But to get the estimate of global average CFC12 concentration, let's pick a value between the Mauna Loa and American Samoa, right here in this white region. So, for example, in 1979, the CFC12 concentration was about 280 parts per trillion. Okay. 1983, we could go up here, and it's gone all the way up to maybe I could say 350 parts per trillion. And so read this data, and we'll enter the values in this table. So I actually just did the first two, 280 parts per trillion, 350 parts per trillion for 1983, that filled in the other 3 years from that data graph. And then you'll be asked some questions here. Questions 2 and 3, I think you can get from the graph. Actually, question 3, let me give you a hint on that. It asks, is the CFC concentration in the northern hemisphere higher or lower than in the southern hemisphere? Well, I think it's pretty clear that it's higher. And why is this true? Well, think about where the CFC factories are and where most people are using CFCs in refrigerators or spray foam insulations and things like that. That's a good hint for that. Here's one that you do need a little bit of a hint on. If the atmospheric lifetime of CFC12 were only a few months instead of 100 years, would the difference between the northern hemisphere and southern hemisphere concentrations be larger or smaller than the observed present observations? Okay, here the idea is right now air mixes from the northern hemisphere to the southern hemisphere, and a little bit of the CFC level is lost during the time it takes to mix over from the northern hemisphere to southern hemisphere, which is usually taken to be about a year. If the lifetime were much shorter, the CFC12 lifetime were much shorter, then much more of it would be lost before it mixed over to the southern hemisphere. So that's a real good hint. We'll see if you can pull it together from that hint. Okay, and then the last question, or last challenge in part one, is to look at this graph here, estimates for total chlorine in the atmosphere based on observations and also model projections into the future. The thing that we're supposed to notice is that this bottom region, magenta color, is flat, and it reads about 0.6 parts per billion all the way over. That flat region is the natural atmospheric chlorine, chlorine from natural sources in the atmosphere. Then chlorine from other sources, the CFCs, and this dark blue region is the CFCs, and carbon tetrachloride and other things, they add up to give the man-made source. So, for example, in the year 1990, actually, maybe 1993 or 94 is where it peaks out here. Okay, during that peak, the concentration of chlorine in the atmosphere, the total concentration of chlorine in the atmosphere, was about 3.7 parts per billion. I'm just reading over here. Okay, of that 3.7, roughly 0.6 was natural. 0.6 out of 3.7 is, I don't know, you could figure it out on your calculator, but about 17% of the total chlorine in the atmosphere came from natural, so the rest, 83%, would be from human activity. That's just my ballpark figure. You're supposed to look at the numbers a little bit more closely, and that's the idea here, is what the total chlorine is, that's at the very peak, in the year 1985 and 1995, what the natural chlorine, okay, these should be parts per billion, I'll change that right now, parts per billion, natural chlorine, parts per billion, which is 0.6, and then the percent of total that is natural, you can just take 0.6 divided by the total, and then to get percentage, of course, you multiply by 100%. Okay, in the next video, I'll give you a little bit of a clue about part 2.